Hello and welcome to this fourth presentation in the series of applying D'Alembert's principle. In the first presentation we outlined the concept. In the second presentation we considered problems involving pure horizontal or pure vertical motion. In the third presentation we considered inclined motion. And in this presentation we're going to consider yet more problems that have been extracted from our workbook. And at this stage of your study, you should be quite familiar with the application of D'Alembert's principle. So within this presentation, I will simply show you the solutions to the various problems selected from our workbook, and then you can review these solutions at your own pace. For your reference, here's the first batch of questions that are considered within the presentation, should you want to jump directly to the solutions. And here's the second batch of questions considered. So let's consider more problems associated with applying D'Alembert's principle. Remember, when analysing such problems, to always draw a free body diagram. When we have forces applied to bodies, we always commence our solution with a free body diagram showing all the forces that are acting on the body. If you need a recap on free body diagrams, there's a presentation devoted to that topic area. So here's the first question I've extracted from our notes that we're going to consider. It's question 10b. A person weighs out diamonds in a lift, which is accelerating upwards at 1.5 meters per second squared. The balance used indicates a mass of 26.5 grams. We've got to find the true weight of the diamonds, and the hint in the question is to initially draw a free body diagram of all the forces acting on the diamonds. And for your reference, that includes the force from the balance on the diamonds. So that force must be added to the free body diagram. And again, a slight conflation between the terms of mass and weight here. The question says find the true weight, but I notice the answer is actually given in terms of grams here. So that's not even the appropriate SI unit for mass. So be careful extracting information from the question, draw the free body diagram, make sure all the forces acting on the diamonds on the body are on the diagram before you begin the solution. And for your reference, the solution to question 10b commences approximately 8 minutes into the presentation. The next question extracted from the notes is question 11f. So the air resistance, labelled as capital R, experienced by a 100 kilogram parachutist is proportional to her velocity. And we're given a relationship in symbol form here as air resistance R is equal to K. K is the constant of proportionality multiplied by V, the velocity. The parachutist's maximum speed is 1.5 meters per second. Note that no acceleration occurs at this maximum speed condition. So that's actually a Newton's first law problem to analyse. The constant K, given in terms of kilograms per second, shown in the bracket here, and here's the acceleration when falling at 1 meter per second. So for question 11f, initially apply Newton's first law for the maximum speed scenario, and then using D'Alembert's principles you can apply the first law to find the acceleration. Question 12f, a 70 kilogram person stands on a weighing machine whilst in a lift accelerating upwards at 1.25 meters per second squared. We've got to calculate what does the person seem to weigh. In other words, we've got to find the force that the weighing machine exerts on the person. So again, you need to draw a free body diagram here and include on the diagram the force from the weighing machine on the person. That will be the effective apparent weight of the person. You can solve that using D'Alembert's principle. Answer is stated in the bracket here. And question 14f, extracted from my notes. When a lady weighs herself in a lift accelerating upwards at 1 meter per second squared, the weighing machine dial registers 77 kilograms. We've got to find her true weight. There's a hint in the question to first of all find the lady's mass. Once you determine the lady's mass, you can then calculate the weight force, shown here in the bracket. And here are the approximate start times within the presentation for the solutions to question 11f, 12f, and 14f. Let's consider question 15f. A person weighs an object in a lift using a spring balance. When the lift is accelerating upwards at k meters per second squared, the object appears to weigh 1.4 kilograms. When the lift is accelerating down at k meters per second squared, the object seems to weigh 1.1 kilograms. we're asked to find the true weight, labelled m0 here, of the object, and the value of the acceleration, simple k. Hint in the question is to generate two simultaneous equations, both in terms of m0 and k. Just note for reference, the answer for the weight m0 is actually stated in kilograms here. And here's the acceleration k. Question 16F. A balloon of total mass, 0.5 tons, is floating horizontally. In other words, that means it's in steady level flight, so it's not accelerating, and Newton's first law applies. If a 100 kilogram ballast is thrown from the balloon, we've got to calculate the acceleration with which the balloon now rises. So as always, first of all, sketch a free body diagram of the balloon, apply the forces in the vertical sense. Don't forget to apply the thrust force from the balloon acting upwards, and using the first scenario of the balloon in steady level flight, floating horizontally, you can find the balloon thrust, and then you can apply D'Alembert's principle to find the acceleration of the balloon in the vertical direction once the 100 kilogram ballast has been removed from the balloon. The upwards acceleration is stated here. Finally, question 20F. A locomotive pulls 3 carriages, each of mass 50 megagrams, and each experiencing the same tractive resistance of 5 kilonewtons. The train is travelling at 10 meters per second, then the brakes are applied, which brings the train to a halt or to rest in 0.1 kilometers. We're asked to calculate the thrust in all of the couplings between the various carriages. There's a hint in the question to make use of an equation of motion, or Suvat equations are sometimes termed, within our solution. So here I would expect to use 3 free body diagrams, firstly to indicate the 3 carriages connected together, so the force required in the coupling for the 3 carriages, then a free body diagram of 2 carriages, and a free body diagram of 1 carriage. And that will allow us to work out the thrust or the force in the various couplings between the carriages. And for your reference, the approximate start times related to the solution for question 15F, question 16F, question 20F are shown here. Okay, as I said at the beginning of the presentation, I'm just going to literally show you the solutions to these particular questions extracted from our workbook. So we commence with question 10b here. Repeated the question for your convenience. And here's question 10b, beginning of the solution, extracting the information from the question. Notice converting the grams to kilograms here. Question 10b, solution continued. Here just converted the mass reading shown on the scales into a force reading in newtons. Question 10b solution. I have actually shown a solution here using Newton's second law. This is the only question in this presentation where I actually apply Newton's second law directly, summation of the force is equal to ma. It's just for you to compare and contrast Newton's second law with D'Alembert's principle for this question. As always, draw a free body diagram here. This relates to the inertial axes, because I'm applying Newton's second law directly here. So on the left hand side of the equation, all the forces applied to our free body, on the right hand side the ma. I will let you review the solution at your own pace. Question 10b, solution continued. Here I am applying D'Alembert's principle, so this is actually Newton's first law now, summation of all the forces equal to 0. Again, I still have a free body diagram, but I've now had to include the inertial force, the ma, on the diagram. That's application of D'Alembert's principle. We're now considering, of course, body fixed axes when applying D'Alembert's principle. The positive direction is shown as upwards here. So this is now Newton's first law applied to the same problem as on the previous slide. It's all equated to 0 here. Again, I'll let you review this at your own pace. Of course, we end up with exactly the same answer for the actual mass. So that's the full solution to question 10b. Here's question 10c I've added into the presentation. It's a very similar problem to that of question 10b. Requires a very similar solution. The question relates to a large skip that's weighed whilst moving vertically in a lift. In this question we have to calculate the true weight of the skip. Answer shown in the bracket here. I'll let you review this question at your own pace. No solution is provided in this presentation. Question 11F, repeated here for your convenience. Here's question 11F, beginning of the solution. As always, extract the information from the question initially. Question 11F, solution continued. Considering the first scenario, when the balloon is travelling at maximum speed, that means it's not accelerating. So we'll be able to find constant K by applying Newton's first law here. Free body diagram shown as always on the right hand side here. Positive direction is upwards for this calculation. So summation of all the forces equals to 0. And the forces applied for this constant velocity situation are the weight force acting down and the air resistance which acts up. We know in this case the air resistance is equal to K multiplied by the maximum velocity. That allows us to find the constant value. I've calculated in terms of newtons per meter per second here, but that does convert to kilograms per second. The answer stated in kilograms per second in the question. Here's a slightly more detailed solution. This is how the unit was defined. Newton can be written as a kilogram meter per second squared. Just note that the per second squared in the numerator here actually is in the denominator, and the per second in the denominator here is actually in the numerator. So now we can see the second on the top line cancels with the squared on the bottom line here, and of course the meters on the top line cancels with the meter on the bottom line. So we end up with the unit of the kilogram per second. That's based on understanding fractions. And for your further information, here's an extract from our previous fractions presentation, where we showed the proof for dividing fractions, in this case dividing fraction AB by fraction CD, can be shown to be the same calculation as multiplying fraction AB by fraction DC. So essentially we have the first fraction multiplied by the reciprocal of the second fraction. In other words, the second fraction C upon D here has been turned upside down here. So applying this principle to the unit problem, we have kilogram meter per second squared as being our first fraction. That's divided by the meter per second, which is our second fraction. So multiplying the first fraction by the reciprocal of the second fraction and cancelling the respective units, we can again show that the Newton per meter per second is the same as the kilogram per second. But that's just for your background reference. Question 11F, solution continued. Now we're considering scenario 2 here. This is where we're accelerating downwards at some acceleration A. We know that the velocity is 1 meters per second downwards. Down is positive on my free body diagram here. So as we apply D'Alembert's principle, we summate all the forces to equal to 0, noting that the air resistance R is actually K multiplied by V. As I said, we know what the K is from the previous slide, and we know what the V is. It's given in this question. So we can work out the downwards acceleration in this particular case. Here's question 12F, repeated for convenience. And here's question 12F, the forward solution. Again, I'm going to let you review this at your own pace. As always, we start with a free body diagram on the left hand side. And I've denoted the force on the body from the weighing machine as P in this case. So you must remember to put that force on your free body diagram, because when you're applying D'Alembert's principle here, force P occurs in the equation. I've actually stated the answer in both newtons and also in kilograms. Here's question 14F, repeated for your convenience. And here's the solution for question 14F. Again, I'll let you review this at your own pace. Always commence with a free body diagram. Applying D'Alembert's principle, what you find you will need to do is to factorize on the mass here. So factorized on this particular line here. For rearranging the first law, we can find the lady's mass, and of course then we can find the lady's weight, knowing gravitational acceleration on Earth. Here's question 15F. Again, the question's repeated for your convenience here. In this question we had a hint to generate two simultaneous equations in terms of m0 and k. So let's review the solution to question 15F. Question 15F solution. Consider scenario 1 first of all. This is where the person accelerating upwards, spring balance reading for the object is 1.4 kilograms. So I've converted that into a weight force here. Draw my free body diagram as always. Have my inertial force applied. So apply Newton's first law because D'Alembert's principle is being applied here. There's two unknowns in this equation, both the m0 and the k value. So I cannot solve the equation. So I will need to generate two equations. So I've rearranged the first equation in terms of k, called this equation 1. Question 15F, solution continued. I then consider the second scenario where the lift is accelerating downwards, and now the spring balance reading for the object is 1.1 kilograms. Again on my free body diagram here, have my inertial force applied again, appropriate direction, and using Newton's first law, because I'm applying D'Alembert's principle, I can again generate an equation which has the two unknowns m0 and k. Again, I've rearranged this equation in terms of k, called it equation 2. So now I will simply equate the equations 1 and 2, and I will solve for m0, and then I can back substitute to find k. So question 15F, solution continued. Here I'm equating equations 1 and 2. That produces a simple equation which I can then solve to find the value of m0. And in this case I back substituted the value of m0, this value here, into equation 2. That allowed me to find the acceleration k in this case. Question 16F, repeated for convenience, relates to a balloon in this case. And question 16F, here's the beginning of the solution. Considering the first scenario here, the balloon travelling at constant height, so steady level flight. There's no acceleration in this particular situation, so I don't need my inertial force applied to the free body diagram shown here. So any force is applied to the upthrust from the balloon, PB, and the weight force from the balloon, which I can calculate knowing the mass of the balloon. It's 0.5 ton or 500 kilograms. Question 16F continued. So applying Newton's first law here, we can determine the upthrust from the balloon. I've called it PB here. Question 16F continued. Here's scenario 2. This is when the balloon is accelerating upwards due to the loss of the 100 kilogram ballast. We know the value of PB, the upthrust from the balloon, from the previous question, scenario 1. We can determine a new weight force because we've lost 100 kilograms balance, so the mass of the balloon now is 400 kilograms. And of course applying my inertial force opposing the change in motion, opposing acceleration here. Question 16F, solution continued. Then by applying Newton's first law, because I'm using D'Alembert's principle, I can evaluate the acceleration of the balloon in the upwards direction. And finally in this presentation, question 20F. This relates to a locomotive that pulls 3 carriages. Each carriage has a mass of 50 megagrams. There's a resistance for each of the carriages of 5 kilonewtons. That's attractive resistance or frictional resistance. And we're also given some kinematic information. The speed of the train initially is 10 meters per second, but it's actually brought to a halt in 0.1 kilometers. So that indicates we need to use an equation of motion, a Suvat equation. So we are asked to determine the thrust or the force in each of the couplings. There'll be 3 couplings to consider here. So question 20F, here's the solution. Extracting information from the question. My locomotive pulling the 3 carriages. Each is 50 megagrams. Don't forget 50 megagrams is 50,000 kilograms. And of course we must include our frictional resistance for each of the carriages. So notice the motion in this case as I've drawn it is from right to left. The deceleration is from left to right. Question 20F, here's the solution. This is for 3 carriages being slowed down by the force from the locomotive. So firstly I've used an equation of motion, given the parameters in the question, to find the deceleration. So it's a negative acceleration here. Question 20F, solution continued. So here's my free body diagram. This is for 3 carriages here. So the force, I've called it P1 here, required to bring all the carriages to rest. The total mass M of the carriages shown here. Total friction force generated by the 3 carriages shown here. As I consider my inertia force on the free body diagram, opposing the change in motion, the acceleration is left to right here. So the MA force is right to left. Newton's first law now applied. Summating all the forces equal to 0, I can determine the force in the first coupling, P1 I've termed it, and that's 60,000 newtons, 60 kilonewtons. Question 20F, solution continued. Undertake the same kind of analysis, this time a free body diagram for 2 carriages, finding force P2 as I've termed it here. Same approach in Newton's first law here. So the force in the second coupling, P2, 40 times 10 to the 3 newtons, 40 kilonewtons. Question 20F, solution continued here. Free body diagram of 1 carriage, finding the force in the third coupling, I've called it P3, which is 20 kilonewtons. So that's the full work solution for question 20F. Here's the bibliography used to help generate this presentation, which I hope has been of some interest to you, and thank you for viewing.